Hello, and welcome to the Future of Safety Science, the webinar series that connects leaders in safety research and standards to the next generation of problem solvers. I'm Dr. Kelly Kina with UL Research Institutes, and I'm pleased to be your host for this series, where we investigate the big questions, beginning with, how is the world engineered to keep us safe? Each episode will extend our work to you through dynamic conversations that will describe our view of safety and sustainability, drill down into specific inquiries and research, and describe the process and impacts of global standards. I'm pleased to welcome our guest moderator for today's episode, Zoe Susice. Zoe is the Director of Research Amplification for UL's Fire Safety Research Institute, otherwise known as FSRI. She was responsible for leading marketing and enabling functions, as well as strategic communications and outreach to amplify the impact of FSRI's research-driven insights. Prior to joining FSRI, Zoe held progressive roles in communications, marketing, and strategy in consumer brands and across the UL enterprise, most recently as Director of Strategy and Marketing for Underwriters Laboratories. She holds a bachelor's degree in business administration from Bucknell University, a certificate from the Yale School of Management for completing the New Science of Marketing Strategic Marketing Development Program, and a Harvard University credential in social media marketing. Zoe, thank you for joining us today.
Thanks, Kelly. It's a real pleasure to be here representing UL's Fire Safety Research Institute, or FSRI. A little bit about FSRI. We advanced fire safety knowledge to address the world's unresolved fire safety risks and emerging dangers. As part of UL Research Institutes, the nonprofit safety science research organization within the UL enterprise, we are committed to sharing our fire safety insights with everyone to advance UL's public safety mission of providing safe living and working environments for people everywhere. Today's episode is a look into the Wildland urban interface, or WUI, and some of our current research evaluating the threats posed to urban interface communities and the built environment by large-scale fires. Due to global factors such as climate change and population growth, wildfires and fires impacting the WUI have become an increasingly global problem. Today's panelists will help us understand this growing issue, how safety science can play a role in mitigating the risk, and detail an example of safety science in action, FSRI's research project exploring structure-to-structure heat transfer in the WUI environment. So let's get started. I'm pleased to introduce my esteemed colleagues for this conversation. First up, Derek Alconis. Derek Alconis is a research program manager for UL's Fire Safety Research Institute. In this role, Derek manages the implementation of organizational initiatives related to firefighter health and safety, and spearhead FSRI's efforts in addressing wildland urban interface, a priority expansion area for our research. Prior to joining FSRI, Derek served 31 years with the Los Angeles County Fire Department, most recently as Assistant Fire Chief in charge of the Air and Wildland Fire Division. During his tenure with LA County, he has helped establish the department as a leader in fireground safety and fire service wellness and fitness. As a firm proponent of training, he has developed and implemented innovative programs supporting fireground tactics, survival, and firefighter health. He is a member of the IAFF and IAFC Fire Service Joint Labor Management Wellness Fitness Initiative Technical Committee and holds a bachelor's degree in biology from the University of California, San Diego. Welcome, Derek. Next up, we have Dr. Gavin Horn. Gavin is a research engineer with UL's Fire Safety Research Institute, and his research interests range from firefighter health and safety and first responder technology development to materials testing and non-destructive evaluation. Prior to joining the FSRI team, he served as the director of IFSI research programs at the University of Illinois Fire Safety Institute, or IFSI, for 15 years, and as a firefighter/engineer with the Savoy, Illinois Fire Department. Gavin holds a doctorate in mechanical engineering from the University of Illinois at Urbana-Champaign, as well as a master's degree in fire protection engineering from the University of Maryland. He has published over 70 peer-reviewed journal articles and given presentations at meetings, conferences, and symposia around the world. Thanks for joining us, Gavin. And then last but not least, Joseph Willey. Since joining FSRI as a research engineer in March 2017, Joseph has been a primary contributor to projects focused on live fire training, fire investigation, WUI, and fire modeling. Additionally, he's developed several tools that have enhanced the team's research capabilities, including a portable measurement system that's used to quantify the thermal exposures experienced by individual firefighters during fireground operations. Prior to FSRI, Joe worked as a fire protection engineer in the Fire Research Division of the National Institute of Standards and Technology, where his work covered research topics related to fire model validation, firefighter personal protective equipment, performance testing, and firefighting tactics. Joe holds a Bachelor of Science in General Engineering from the University of Illinois at Urbana-Champaign and a master's degree in fire protection engineering from the University of Maryland.
All right, well, I'm going to start off. My name is Derek Alconis, Research Program Manager with Fire Safety Research Institute. As was mentioned, I have experience within the fire service and within the wildland urban interface fires in particular. I'm going to focus my comments on wildland firefighting, WUI firefighting. We'll have to start by defining what interface and what intermix is. Interface is when you have a community of homes, a neighborhood of homes, you can imagine, that is tucked up against the wildland vegetation. And an intermix is when you have houses that are dispersed within that wildland vegetation. And an interface is where, mostly you have a large loss of fires. When we see these fires on the news, it's normally due to a number of homes catching fires within the interface. Now, before I show you a video of actual firefighters engaged in a wildland urban interface fire, I wanted to describe the conditions that create these conditions where you have a large loss of structures. And in California, every fall, we have a high pressure system that develops over the Great Basin. And then you have this low pressure system that develops over the coast of California. And the differential between that high pressure and low pressure system creates wind. And that wind gets hot and dry as it goes through the desert. And as it passes through the passes or the canyons and the drainages and the valleys of the Sierra Nevada mountain range, of these local mountain range along the coastline, and you get a funneling of that wind, which intensifies it. And you can have at times 50, 70, even 100-mile-an-hour winds in the fall season. And in this particular satellite image, you see I have Paradise and the Camp Fire up in Northern California and the Hill and Woolsey fires. These are actual satellite shots that were taken in November during the active portions of those fires. And those are smoke plumes that you're looking at there. And we're going to take a look more in depth at the Woolsey fire, because that's what I have a video to show you of. And I was there myself for about 2 weeks. And the Woolsey fire started in this area where the arrow starts there. And so you can say it's a certain distance from the California coast. And where it started was vegetation that hadn't burned in quite some time. And keep in mind, during that time of year, in the fall, you have very dry vegetation. On this particular day, the live fuel moistures were critical, at 60, even less than 60% in some areas. And you also had a relative humidity that was in the single digits. You had winds at 70 miles an hour, and you had vegetation that hadn't burned. In some areas, we didn't even have a burn history on it, which means it could be over 100 years. But a lot of the vegetation that you see in this burn scar here of the Woolsey fire was 15 to 30 years old, which means you can have vegetation that's 30 feet tall in some areas. So you think about, a 30-foot tall piece of brush that is subjected to these hot, dry winds. All you need is a start to get things going, and it's really going to be off to the races. And that was certainly the case in November of 2018. So this is a satellite shot on the left here, and you can see the 101 freeway cutting through. The fire started just north of that. This actually shows you the burn scar of the Woolsey fire. And what you also see is the interface. I like this picture because it really shows that really well. And as the fire dumps into these vegetative areas, it's going to burn up through these canyons, going to run up the canyons actually, and impact these structures. All where my cursor is kind of showing you here, those are all interface area. Now, what you don't see, because it's so far panned out so far, is the intermix structures, which there's quite a few in this area as well. And you can see all of this is interface down here on the south end, but you got firefighters in those areas. And there was a wall of fire rolling through this vegetation. I mean, it took less than 10 hours for the fire to get from the north to the coastline. This is on the right-hand side is a more detailed view of Point Doom, which is this area right here. So this is Point Doom. And you see there's some drainages that run through this neighborhood. And in those drainages, you had an ember cast that started those fires. And keep in mind, when you've got vegetation this dry, 70-mile-an-hour winds, you're going to be throwing embers a mile ahead of the fire's front. So, you've got smaller fires starting in these canyons, running up the faces of the drainages and impacting the homes that lie right in the interface, hence the problem. And this is a shot of at the end of the fire where, this is the actual fire's perimeter. When they map it out, that's what it was shown to be. That's where the black was, if you will. And in amongst this is a lot of burned out structures. The Woolsey fire burned over 1,000 structures and about 100,000 acres. So now let's go deeper. Let's look at the actual fire itself. Let's see what the firefighters were experiencing. When you have that mass of vegetation burning in a neighborhood, several different neighborhoods, firefighters are required to defend the structures that they can. Here's what it looks like. Here's what they're experiencing.
It was fairly remarkable how fast the fire was moving. When we were patrolling that area in the early morning hours, I remember at some point remarking to Chris, "Hey, you realize it's 10 o'clock in the morning?"
Visibility, I would say, was probably just maybe 5 to 10 feet out in front of the truck. And what we could see through the smoke was just balls of orange, which happened to be bushes, trees, or structures that were on fire.
So those first images were taken during the morning time where the sun was out. You should be able to see no problem. Day turned to night.
Fire activity and now infrastructure now. You're looking at the clock and the clock says 11:45 and you're looking out the window and it's midnight.
So as you look at these images, you begin to think, wow, how can anything survive in those conditions? At FSRI, we're interested in how the fires progress in those environments. and how firefighting can impact the defense of those structures, and also keeping the firefighters alive, which is really important, of course. In June of 2022, the U.S. Fire Administration published this report. They look at the issues and the resolutions regarding wildland-urban interface fires. These are some of the things that were mentioned in this report. It mentions that the WUI area has seen exponential growth, especially in the period of 1990 to 2020. That's 20 years experienced a 43% increase, or about 8 million new homes just in that period. It also mentions that human-caused wildfires have tripled the length of the wildfire season and tend to be more destructive because they're more likely to occur near homes in the WUI. And you look at how fires start in these areas, 89% nationwide, they're human caused. And in California, it's approximately 94%. So as we expand into the WUI space, we increase the risk of these fires occurring, and especially when those dry, hot winds develop in the fall season, especially in the western part of the United States, where you have these, very dry vegetation and these high wind conditions, and a big population that's living in those areas. It's imperative that the WUI areas, these communities, they work closely with the wildland and local fire departments to take steps to reduce the wildfire risk. And we're right there with them too, as FSRI, I might add. The report also says that between 2005 and 2020, wildfires destroyed more than 89,000 structures in the United States. It's just an amazing number. And the most damaging wildfires have occurred just in the last few years, accounting for 62% of the structures lost over the last 15 years. Now, even though we're the most developed society that ever walked the earth, yet we are losing to fire. In addition, as America's WUI continues to grow by approximately 2 million acres per year, we know this, conditions will only become worse. And it's estimated that there's, about almost 100,000 people that live in the WUI, whether it be intermix or the interface. So what is this? I mean, what is the stats? So I pulled some stats from California. In fact, Cal Fire publishes this every year. And it's a look at the historical fires that have occurred in California. The largest fires by acreage, the most destructive fires by structures lost, and the most deadly fires by the number of lives lost on a structured fire, on a fire. And on these wildland WUI type fires, you can see that, there's the Camp Fire, 18,000, and the numbers are just staggering. But really, when you look a little closer at the dates, the last 5 years have been devastating. When you look at the number of structure fires, the last 5 years, the number of WUI fires that have destroyed the most structures, the last 5 years have been incredibly devastating. 13 of the largest structure loss WUI fires have been within the last 5 years. This points to the fact that there's still a lot to do.
So as you can see, WUI fires present a big and important problem for the safety of our communities. That includes the people who live in those communities and the places that we call home, and a problem also for the environment. And this is a place where safety science has played an important role in understanding how we can combat some of these risks that are posed by fires in the wildland-urban interface, but also some of the research and studies that's necessary to continue to improve the safety of those who live and work in the wildland-urban interface. So we want to drill down a little bit on what safety science is needed. And we want to think about what we want to protect through safety science. And Derek provided a great overview and some stunning videos and pictures that show the need to protect the people, the places, and the things that are in the wildland urban interface. But when we think about the people, we have to understand it's those who live there who may be directly under attack from those wildland urban interface fires, the flames and the embers and the smoke, but also those who may be a distance away. We also need to think about the firefighters who are coming to work and to help those individuals to try to suppress the fire or to contain the fire, or in some cases help to evacuate the communities which are under attack from the wildland urban interface fire. When we think about places, we often immediately turn to the homes where we live, but also need to understand how to protect the businesses and the infrastructure around the commercial interests and the industrial properties, as they may be protected differently than the residential structures. We also need to think about the things that exist there that help to support the communities, places where you congregate, places where you might recreate, all might be impacted differently by these fires. We often don't think about things like the water distribution system or the sanitation system, but those too must be able to be protected in different ways. And there's certain science that's necessary in order to understand how to protect those things, but also bring them back online when individuals return to the communities where they live and where they work, so that there can be resilience among that community and they can get back to their normal life as quickly as possible after the fire has been addressed. We also need to think a little bit about what we want to provide protection from. And often when we think about this, the first thing that jumps to mind is the hazards related to the flames. It's the first thing that jumps out from the pictures and the videos that we see around the wildland urban interface fires. And the flames can provide a lot of different types of risks and a lot of different length scales and time scales that we need to protect the people, the places, and the things from. Direct flame contact can start to ignite and to damage structures in the immediate vicinity. But we know in addition to the direct flame contact, there can be radiation that might extend tens or hundreds of feet away in terms of the damaging capability, in terms of being able to damage the structures and potentially even to ignite some of those structures. So we're concerned not about just the direct flame contact, but those tens to hundreds of feet away where the flames can cause some damage. We're also interested in smoke. We're developing a lot more understanding about the smoke. It's the other thing that you see in images like this quite regularly, where smoke can be rolling over these hills. The smoke can be directly and acutely impactful to anyone who is in that wildland urban interface during the fires. How do we help get those individuals out so that they can breathe fresh air and they can then not have the direct impact on their airways from the smoke? We need to be able to protect the firefighters who will be going into these areas, as the other responders, such as police and the emergency medical services, who might have to be working in the smoke for days or weeks, and possibly some cases even months, depending on the extent of the wildland and the wildland urban interface fire. We also need to understand that this smoke can travel miles away from the actual source itself. In 2020, we had a large fire here in Oregon in the Labor Day weekend. And I received phone calls from family back in Illinois and coworkers all the way into Maryland about the smoke that had reached all the way across the country and had been affecting their air quality in those areas. And the other hazard that we need to think about at different length scales and time scales are the embers. And these embers Derek talked briefly about. This is a great image. It shows these small pieces of material that contain a lot of energy. They've broken off from some initial material that was on fire, and they may be flaming or they may be smoldering, but these things can carry some energy with them. And the length scales that we're concerned about, these can be from immediately near what's burning, where small pieces, say, of vegetation may break up and pile up next to a fence and ignite a fence or ignite a wall or ignite a deck. As Derek mentioned, they may also, depending on their geometry and the wind condition, become airborne and then move for miles away from where they were initially formed. And we need to think about these at multiple different locations. We have to protect the people and places and things from the flames and the smoke and the embers, not just in the wildland urban interface, but also in the areas where they might be evacuating, as you can see here along the roads where visibility can be impacted, where additional flame contact or embers may begin to ignite some of the areas around there, while those who are affected by the fires may be evacuating, but also where the firefighters and emergency responders are going to be responding to that area, as well as to very distant communities, as I just mentioned, where the smoke impact can travel miles, hundreds of miles, maybe even thousands of miles, to impact those who are working or commuting in these distant communities. So we can see that to address these concerns, we've got a range of different risks and length scales and time scales that we need to be concerned with. And the safety science community is looking at these through a wide range of different technical disciplines. One that we focus on at FSRI is really through the engineering pathway. Many of us are fire protection engineers. They also have backgrounds in mechanical, chemical, civil, or environmental engineering, and work with others in various scientific disciplines, from the traditional math and physics and chemistry to data science, which Derek shared a little bit about data science, and atmospheric sciences, and how they can all come together to help the engineers to understand some of these risks. The huge amounts of data we have available, we can gather information from the boots on the ground all the way to the satellite imagery that can help inform the fire service on how to respond and the engineers on how to protect our communities. And we also need to interact and collaborate with those in the medical community, understanding how we can reduce some of the impacts on the environment as well as on the individuals who live or work in these communities and the surrounding communities, through community health, through industrial hygiene, and other aspects of the health infrastructure that are critical for us to work with. And finally, we need to work with those who are communicating and planning the emergency responses and planning the communities of our future, so that we can learn how to harden the structures so that we can reduce the risk, but also improve the ability for individuals to evacuate while our firefighters and our responders are moving into these areas. Now, in our time together, we can't possibly cover all of these disciplines and how they work together for safety science. But Joe is going to take you through a project that we're working on at the Fire Safety Research Institute, where we apply safety science to the wildland urban interface fire risks. So Joe, take it away.
As Gavin and Derek mentioned, there's still a lot of research that's needed to be done in terms of WUI fires, and this problem isn't going away anytime soon. It's actually getting worse, as Derek showed. So one of the projects that we're doing at FSRI that we're currently in the middle of, it's a 3-year project that's related to WUI, but also has applications outside of WUI. We're focusing on structure to structure heat transfer and fire spread. So as Derek was mentioning, a lot of the losses from these big WUI fires happen once the fire reaches that interface between the wildland and more urban or suburban areas. And then once the fire gets into these communities, it travels not necessarily through just firebrands and or embers like it normally would in the wildland setting, but also from structure to structure, more of a radiative heat transfer and fire spread. So we're, I guess the overall goal of this project is try and figure out how to make structures more resilient so we can increase the likelihood that not just structures, but whole communities are able to withstand these types of fires, and we can reduce the large losses that we see with these kinds of fires. So like I said, we're in the middle of this project, so we're on year 2. So I'm just going to go over the experiments we've done so far and kind of hit on some of the key results, and we'll go from there. So last year was our first round of experiments, and we basically had 3 different sets. We started out in phase 1, where we exposed a whole bunch of different building materials, roofing materials, decking materials, different siding materials to a heptane spray burner, which is a well-characterized heat source. And we set these small samples different distances away from the fire, so we were exposing them to different intensities of heat flux, and heat flux is just the amount of energy from that fire per unit area. And then once we kind of got an idea of those materials' critical heat fluxes, when they started to deform, melt, ignite in some cases, we moved on to phase 2, which looked at a compartment fire with a facade attached to the compartment. So this was kind of to simulate fire progressing from the interior of a structure to the exterior of a structure. And during these experiments, we were looking at characterizing this source fire by measuring the heat flux at various distances. So you can see in this middle picture here, these towers, and those are all heat flux gauges. So we're measuring the exposure from the fire over the course of the experimental duration. And then another thing we're looking at is different siding materials. So different siding materials on this facade and what their contribution is to the measured exposures. Or in other words, if one siding material contribute or has a higher exposure, causes a higher exposure, more intense fire than other types of siding material. And then finally, in the third phase, we looked at the same source fire with the facade that we characterized in phase 2, except for now we introduced a target structure across from it to kind of simulate not only with the source fire, a fire going from the interior to the exterior of a structure, but then also having a neighboring structure across from that and seeing if we could get some fire spread from that to the target structure. So we'll go into a little more detail about phase 3. So like I said, it's meant to simulate 2 structures that are neighboring. The source one is on fire, and then you have your target one. And we were looking at a whole number of things during these experiments, including looking at different siding materials on that target structure and how they behaved when they were exposed to the source fire. And then we also, if you look closely, you'll see in an upcoming slide, but we have windows in this target structure. So we are also looking at window failure, how they fail, when they fail, once they fail, if embers or firebrands or just fire itself could get through there, and that would be a failure point on the structure. So if you think of it as an actual neighboring structure, there's fuel inside that house. If a window breaks and embers and firebrands start getting in there, that's going to ignite the contents of that room, and that house will start to go, and it's just kind of a chain process from there. And then the third thing we looked at was putting intermediate fuels or ladder fuels in between the 2 structures and seeing how, if and how they contribute to fire spread from the source to the target. So this is just a quick slide showing the different types of siding material that we looked at. We looked at vinyl siding over expanded polystyrene, T111, which is a wood siding, and then fiber cement board lap siding, which is a non-combustible type of siding. And then for our ladder fuels, we looked at 3 different types. We looked at a shed in between the 2 structures. We looked at a car, which just happened to be a PT Cruiser, in between the 2 structures. And we also looked at an attached deck between the structures. So again, these are common things that could help propagate a fire from one structure to another that you would commonly see in between residential structures in a community. This is a quick video of the deck experiment with the ladder fuel. This was the one experiment where we got the target structure to ignite. So if you look, we have an overhead view here, and then you're looking at the target structure in the deck at this view, and then these are just side views. And this is the source, looking at the source compartment. So I'll go ahead and play this, and you can watch the, this is shortly after flashover. So that's essentially when the compartment goes from having a fire inside it to everything in the compartment being on fire. It's a good marking time. During this project, we're focused on post flashover exposures specifically. So you can see shortly after flashover, the deck ignites on the front. And then as you continue to watch, you'll see it propagate across the rail. And then eventually up the siding. The siding in this case was the T111, or that wood base siding. So it ignites pretty quickly once it gets going. So just some quick takeaways from phase 3 that helped drive our plans for the 2022 experiments that I'll talk about in a minute. The only experiment where we got the fire spread to the target was when we had the deck, which was attached to the target. And then we also observed some significant pyrolyzing of the T111 when we didn't have a ladder fuel in between the two structures. And it almost looked like it was going to ignite, but we were actually kind of testing the capabilities of our lab and had shut down our experiments before we could see what actually happened. And then we also saw some interesting window failure, which brings me to the experiments that we conducted this year. We actually just finished them a couple weeks ago. And they're looking at those last 2 bullet points on the previous slide a little closer. So we're looking at, again, different siding materials. It's a similar setup as the phase 3 with the source compartment and then a target structure. So the top picture is the first round of experiments we did. You can see that we're just looking at basically a big wall or big facade with different siding materials on it. And then in our second round of experiments, we looked at various types of windows, which I'll get into in a second. And again, the fuel load is similar to what we had when we did our experiments in 2021, except for we have more wood lining the walls and ceiling, so we have a longer burning duration. And what we're kind of investigating based compared to the 2021 experiments is that we're looking to go for a longer duration after flashover, longer exposure duration, and then we're also looking at smaller separation distances between the structures. So in phase 3 of 2021, we did 16 feet between structures, but it's been noted in several documents that these new communities that are getting built can typically have separation distances as small as 6 to 10 feet between structures. So we kind of wanted to look at closer separation distances and how that affected things. So we looked at similar siding assemblies that we tested last year, with one exception. We swapped the vinyl over expanded polystyrene for EFIS. So that's here on the left. And then you have your T111 again, a wood siding assembly, and your fiber cement for the non-combustible siding. And if you look, so not only are we looking at the behavior of these sidings at different separation distances, different intensities of exposure to the source fire, but these experiments also allowed us to characterize the heat flux that we saw from our source fire and get a really good idea of not only the distribution across the target wall. You can see these little dots on each wall. Those are actually heat flux gauges. So we're measuring the heat flux to the target wall at 12 different points across the wall. But then by the end of these experiments, we have data sets that are 12 heat flux measurements, or heat flux measurements from 12 points across the wall. But by the end of it, we also have it at different distances. So similar to what we did with phase 2, we're characterizing the exposure that we see from our source compartment with these experiments. And then with round 2, like I said, we were looking at windows. So we looked at 4 different window assemblies, basically different variations of tempered and plain or annealed glass. So tempered glass is a little stronger, it's been treated, and it's a little more durable. So we looked at both panes being plain glass, both panes being tempered glass, and then outside tempered, inside plain or annealed, and vice versa. So there's some codes out there that say recommend, and other documents that recommend if you have a double pane window, having one of the panes tempered, but they never really specify if it should be the outside pane or the inside pane, or if there's a difference between them. So that's one thing that we were looking at. And then we also conducted 8 of these experiments. So we got a lot of replicates of all these different types of windows being exposed to the source fire. This is just a more detailed or closer up view of our target structure. You can see we have even more heat flux gauges than round one. We have 15 now on the target structure. And with these, each window is surrounded by gauges. So we're able to estimate based on those measurements what the actual glass on the window is seeing in terms of an incident heat flux. And then we also have heat flux gauges behind the windows. So we can measure the heat flux transmission through the window and see if there's any differences between the different types of window assemblies. And like I said, we just finished up these experiments a couple weeks ago, so we're still in the very early stages of data analysis. But one thing that we observed over the course of these window experiments that's pretty interesting is it seems there is actually a difference between whether you have the plain glass, if you have one pane plain glass, one pane tempered, there is actually a difference depending on what orientation you have them. So you can kind of see in these two pictures here. On the left, you have the tempered on the outside and plain on the inside. And so what would happen would be that you would still get heat, you still have an exposure to the plain, even though it's on the inside. And the plain glass is not as durable as the tempered, so that would crack first, and then the tempered would go. And tempered glass, if you've ever seen it break, is more of a catastrophic failure than plain glass, which is just kind of cracks and then eventually they fall out of the pane. The tempered glass is the more catastrophic failure. So that shock from the failure actually causes the plain glass pane to fall out and then leave the big hole there for all sorts of embers and fire brands to get in. And then on the other configuration where you have plain glass on the outside and tempered on the inside, we did not see that result. And then here's just a quick video of what I was talking about. So this is a camera view from the backside of the windows. And you'll see the plain glass crack first and then the tempered go. And when the tempered goes, a big hole is formed.
Bottom inside pane. BL bottom inside pane.
2 minutes after flash.
BL tempered bottom.
And again, this was kind of consistent across our experiments, where we would see that this configuration of tempered on the outside
Tempered.
and plain glass on the inside did not provide as long of protection as the other configuration. And with that, I just want to give a quick thank you to everyone for taking the time to listen, and special thanks to everyone who helped plan this webinar.
Thanks, Joe. I'd like to offer you to stay on screen and welcome Gavin and Derek both back as well, because with all of that wonderful information that the three of you just shared, you can imagine there are quite a few questions about the research, but also about the paths that the three of you have taken. So I'll go back to Joe for this first question, but Gavin, Derek, feel free to jump in if you have some supplemental information to add. So Joe, with a research project like this, you mentioned at the beginning that this was a 3-year project. What goes into planning and executing something like this that kind of makes it take that amount of time?
Well, it's a huge process, starting everything from planning your experiments. What exactly do you want to do? What are you trying to accomplish with your experiments? What are you investigating? All that. Once you have a plan in place or a solid plan, you have to find a facility to do it at. So in 2021, we're able to use UL's fire lab. So we had indoor testing, but then in 2022, again, in part due to some of the limitations that the lab had with their exhaust system, we decided to take the tests outside and burn at the Delaware County Emergency Services Training Center in Delaware County, Pennsylvania, which we do a lot of our burning at. But yeah, so you have to find not only a setting for it, but then you have to figure out what kind of resources you need. Everything from instrumentation to tools and whatnot. We have different stashes of these. We actually have a big trailer that we run a lot of our data out of and experiments. But so I guess to short answer to your question is it takes years and years before the project itself to make it run smoothly and I guess as smooth as possible. And it wouldn't be possible without a team of great engineers and project planners to help us.
Gavin, kind of what drew you to pursue fire research and safety science? What has been your career progression getting into that?
Well, I guess, first of all, what drew me to doing this type of work was the possibility for impact. Everything that we just discussed in terms of the risks that communities face and that people face from fire, and the opportunity to help to reduce some of those risks. There's a lot of different ways that engineers can impact the world, and fire protection is one of the ways where we know there's a problem that exists that we live with. We have fire that can create risk in various different ways, and there's different ways that we can address that, by hardening structures, by changing the way that we live, by helping to improve the fire service. And there's a lot of different things that we need to understand before we can put them into place. So by setting up research studies to try to address some of these concerns in as controlled an environment as we possibly can, we can learn a whole lot more about them and try new things out before they can be implemented into the real world. So the ability to have an impact on the safety of individuals for a risk that exists everywhere within the world. Fire is a risk in every community across the country and around the world. The risks might be a little bit different, whether you're living in the wildland urban interface or living in a city, but we all are facing some risks from combustible materials coming in contact with a flame that can change the environment with which we live. So I would say that you have an opportunity to make an impact, and being able to work in this community, in this safety science community, has been very, it's been very helpful to understand how we can better society through our science.
Yeah. And you mentioned a little bit in your part of the presentation about the different types of disciplines that are needed or could help address the safety science issues. I know at FSRI, we do quite a bit of collaborative research. Can you talk a little bit about some of those disciplines and maybe even provide an example of how we've brought together different disciplines or different specialties to address fire safety?
As the risks that we face become more complex, the answers are also more complex, and the different expertise that are needed to understand those risks becomes more multidisciplinary. So one example from a study that we conducted at FSRI was looking at risks that firefighters face when they're responding to structure fires. And we've often developed our personal protective equipment and a lot of our response capabilities focusing on the thermal threat. So the heat that's transferred from the fire, the high temperatures with which we're working. But we've come to understand that there's also concerns about the smoke and the long-term impacts of exposure to smoke in those environments. While the fire protection engineers and mechanical and civil engineers, where we traditionally work with, understand a lot about the fire and the fire in the environment, we also are able to work with individuals in industrial hygiene who understand a little bit more about the chemicals that are produced, how they impact the working environment, and then the occupational exposures for individuals that are working in that way. And then we also work with those in exercise physiology who understand how difficult it is to do heavy, strenuous work while you're wearing fully encapsulated personal protective equipment. In some case, very heavy PPE, such as the bunker gear that firefighters wear. So the engineers can, again, focus on what's being produced by the fires, but the exercise physiologists and industrial hygienists can help us to understand what happens to the individual who's working inside that gear as they're responding to these fires. And while much of this study is focused on structural firefighting, we have some of the same concerns with the wildland urban interface fires. We have different types of fires. We may have different things that are burning, and there may be different personal protective equipment that is being worn. But we need to continue to bring together people from many different disciplines that can help us look at these problems from these different perspectives in order to get the best answer that we possibly can.
Great, thank you. So going over to Derek, having been one of the people that has spent a career kind of wearing that PPE with this impressive tenure at LA County over 30 years, what made you look to FSRI, the Fire Safety Research Institute, as the next chapter in your career, Derek?
Well, I think the data speaks for itself. I mean, what I presented up there was the facts of the condition of the planet and us who occupy it, right? I mean, it's just the devastating effects of fire would show that we need to do something more to understand it, how to coexist with it, and maybe how to use it to our benefit. Some of these conditions that we're living in, we've created it ourselves. And so my interest is there's a lot of problems out there to solve. And if you just look at fire, there's so much out there. And we're just looking at wildland urban interface fires right here. But Gavin mentioned a lot of other areas of fire that need to be investigated as well. And so, I mean, how can you, it's weird when if you end a career and you're like, yeah, you're used to fighting the fires and organizing resources and people to go out there and defend communities from fire. But it's not over. It's like, there's still so much unresolved issues out there. And I feel so fortunate to be with the Fire Safety Research Institute to be able to continue to discover ways to address the threat and to maybe create some, not maybe, we are going to create resiliency, you know, in the things we touch, whether it be building construction or providing a better PPE ensemble. We're understanding those things more, and there will be discoveries that will improve our living condition or our ability to fight these fires more effectively. So I just want to be there and help any way I can.
So going back to Joe, you've had a bit of a different path than Derek. Can you talk to us a little bit about your career progression to date?
Sure. So basically, when I was in high school, I did what a lot of high schoolers do, and not really have any idea of what you wanted to do, but go to college for something. And I've always kind of been a tinkerer and liked math and science, so I thought engineering was good. But the idea I had in my mind was that would be my fallback, and I would become a full-time firefighter after I graduate college. And then I started volunteering my freshman year in undergrad. I went to the University of Illinois, and through a couple of different means, ended up getting into contact with Gavin, who at the time was the director of the Illinois Fire Service Institute. And he was doing some really cool research that caught my eye. And I just started working with him, and things got more and more interesting. And I was familiar with some of the work, but definitely not all of it before meeting with Gavin. And I guess I've been hooked ever since. So through Gavin, I was through Gavin, I was told about an internship opportunity, or a summer internship opportunity at the National Institute of Standards and Technology, or NIST, in Gaithersburg, Maryland. And so I spent a summer out there, and another summer, and then eventually, once I graduated, while I was going to grad school at Maryland for fire protection engineering, I was also working full-time at NIST. And then kind of as the research from NIST, the firefighter research from this kind of transitioned over to FSRI, the group at UL. I was one of many in that transition over to UL.
Well, thank you, Joe, for that. And thanks to all three of our fabulous presenters and panelists from FSRI. For more information on the work of Gavin, Derek, and Joe, as well as the rest of our FSRI team of researchers and communicators, visit us at fsri.org, where you can get firsthand view of all of our projects and all of our programs, including things like internships and fellowships with FSRI. Thank you.
Thank you for joining us for today's wonderful episode. And thank you again to Zoe, Derek, Gavin, and Joe for today's presentation, and also for the incredible work that you do. To find more of these dynamic conversations, you can go to ul.org or find us on our YouTube channel called The Future of Safety Science. We'll see you there for more ways to discover the fascinating world of the science of safety.